Hello everyone, I'm Sonjoy Dey. I'm currently doing my master's in the Department of Mechanical and Nuclear Engineering here at Kansas State University. My advisor is Dr. Gurpreet Singh. Today I'll be presenting about nanosheet reinforced polymer-derived ceramic fiber mats. I'm originally from Bangladesh. I received my bachelor's in mechanical engineering and arrived here in the US in the last semester in the midst of pandemic. Bangladesh is shown here on the map. Today, I'm going to talk about some of the preliminary results related to nanosheet reinforced polymer-derived ceramic fiber materials, which was done in the previous 3 months. To give you an outline about the research, firstly, I will talk about the objectives of this research, then I'll move on to the motivation behind this research, then the materials used for this research, then the experimental approach, then the analysis done via microscopic and spectroscopic technique, and lastly, I will conclude some remarks and highlight on the future works that is based on this research. So the objectives of my master's thesis research is to understand the influence of introducing exfoliated nanosheet material on different properties of polymer-derived ceramic fibers. So the primary motivation behind pursuing this research is the advancement in synthesis and introduction of nanomaterials into carbon fibers, as well as polymer-derived ceramic composites. Shown here are three such examples. Example one is the most recent work in which the authors introduced graphene, which is a type of 2D material, into polyacrylonitrile precursor to make graphene reinforced carbon fibers. Authors reported 3 to 4 times enhancement in modulus and breaking strength as compared to neat carbon fibers. More importantly, this work was published only last year and also in Science magazine. Even more importantly, such enhancement was observed in very low weight loading of graphene, which is 0.05 weight%. Likewise, other kind of nanomaterials, for example, carbon nanotube were introduced into polymer-derived ceramic silicon carbonitride bulk material, which is shown here. And exfoliated boron nitride was also introduced into silicon carbonitride, which was also from our group, which is shown here on the right-hand side. Inspired by all of this work, I have pursued a new type of 2D nanomaterial, which are transition metal dichalcogenides or TMDs. To talk about the materials that was used for my research, here's the precursor for the polymer-derived ceramic that was used. It is named 4-TTCS. To elaborate, it is 1,3,5,7 tetramethyl 1,3,5,7 tetravinyl cyclotetrasiloxane. This precursor was studied in past by one of our group members, Zonkan, to prepare silicon oxycarbide's electrospun fibermats with the help of a spinning agent. Now, to talk about the nanosheet material or TMDs. So TMDs are generalized by the formula MX2, where M stands for transition metal, which is situated here in the periodic table highlighted, and the two chalcogen atoms, which is highlighted here on the periodic table. So TMD is a nanosheet material which has similar sheet-like structure of graphene. In addition, TMDs have oxidation temperature which is higher than that of graphene, and moreover, the mechanical properties such as Young's modulus of monolayer TMD material is comparable to that of steel. As there are 40 different type of TMDs possible with the combination with transition metal and chalcogen, we get versatile chemistry. And among all of these TMDs, my study will concern on molybdenum disulfide, which is one of the most studied TMD material. So moving on to the preparation of nanosheets of TMD materials containing fibers is a multi-step process, and the step one includes exfoliation of such TMD material. The TMDs are available in bulk powder form, or sorry, I meant form, which has to be mixed with a solvent such as isopropanol and sonicated with Horn sonicator. The tip of the Horn sonicator generates ultrasound, which creates cavitation with high kinetic energy or surface energy, which peels off individual layers of sheet of TMDs. Here you can see the action on the picture. By sonication of this solution, we get ink-like solution of MOS2. This solution is then mixed with a spinning agent, which is named polyvinyl pyrrolidine, and then it is mixed with polymeric precursor 4-TTCS to get the final solution. The final solution is then poured into a syringe, and then the solution is electrospun. Assuming that everyone here knows about the electrospinning process, I'll move on to the Fibermat, which is obtained from electrospinning. Then this Fibermat was cross-linked at 160 degrees Celsius for 24 hours in the presence of air. Then a small part of it was pyrolyzed in 800 degrees Celsius for 30 minutes in the presence of argon. So for the analysis part, here are the microscopic images of the Fibermats. The scanning electron microscopy microscopic images of the pyrolyzed MOS2 SiOC fibermats released fibermats showed that the fibers were uniform, no beads or anomalies were observed. The TM images or transmission electron microscopic images of the cross-link and the pyrolyzed fibermats were also observed. From there, we see that the fibers are solid. The diameter of the cross-linked fiber was on average 4.36 micrometer, and for the pyrolyzed sample, the fiber diameter was 1.71 micrometer. So the spectroscopic analysis was done via Raman spectroscopy, where we can observe in 375 centimeter the in-plane active mode of E12G bulk crystal for molybdenum sulfur bond, and also in 400 per centimeter the out-of-plane vibrational mode, and also a peak at 440 centimeter for molybdenum sulfur vibration. So this confirms that molybdenum was present in the Fibermat. There was also D and G peaks observed in the Raman spectra, which confirms that there are free carbons available in the sample, which is analogous to the previous studies done. To move on to the next spectroscopic technique, to be specific, Fourier transform infrared spectroscopic technique, it was done where we can see from this figure that pre-ceramic polymer 4-TTCS is going through cross-linking and pyrolysis. To be specific, here vinyl polymerization is at play, and in the cross-linked and pyrolyzed stage, hydrogen containing chemical groups are disappearing. The silicon oxygen and silicon carbon stretching seen at the pyrolyzed stage is typical of the PDC material that was studied in the past. To conclude, the yield of the fibermats during cross-linking and pyrolysis steps have been found out. The morphology of the Fibermat, which was studied with scanning electron microscopy and transmission electron microscopy, showed uniform fibers along the length, and the average diameters were also calculated. The Raman spectroscopy revealed free carbon phase in the Fibermat, and the FTIR analysis revealed the cross-linking reaction that was occurring during different stages. To highlight about the future works, in future, I want to find out about the yield of the nano-sheet material, which is in the as spun Fibermat. I also want to find out how does the mechanical properties of the pyrolyzed ceramic Fibermats change or evolve as a function of different weight loading of nano-sheet material. I also want to find out the applications of as prepared SiOC Fibermat in CMC composite. In addition, I want to find out the application of these Fibermats in electrochemical devices for energy storage applications. So thank you all for being present in this presentation. Bye everyone.